These programs are distributed under a Creative Commons Attribution, Non-Commercial, No Derivatives license. You may copy and distribute these programs free of charge. You may not sell them, and you may not alter them. These programs are part of a study examining the value of podcasting as a medium for medical education. If this is the first time you are viewing a program in this optics series, send an email to jyoungmd@gmail.com with your name, position, institution, city, state or province, and country. Thanks, and enjoy the podcasts. Today's lecture deals with focal points, focal lengths, and ametropia. And I think that you'll soon see that they're in fact all one topic. With focal points, we're just going to have to memorize some things here. The primary focal point is the point from which rays of light emanating upon striking the lens will emerge from the lens with a zero divergence. So the primary focal point for a plus lens is to the left of a lens, and the primary focal point for a minus lens is to the right of the lens, because rays of light must already be converging when entering a minus lens to emerge from the minus lens with a zero divergence. The secondary focal point, which is designated by F prime, the primary focal point was designated just by the capital letter F. The secondary focal point is actually a little bit more relevant to us clinically. The secondary focal point is the point of convergence where rays of light enter the lens parallel. They enter with a zero divergence. Where those rays of light converge, that's the secondary focal point. So the secondary focal point for a plus lens is to the right of the lens, and the secondary focal point for a minus lens is to the left of the lens, abiding by our convention of rays of light moving from the left side of the page to the right side of the page. Okay, let's talk about ametropia. In ametropia, in which a patient does not need spectacles in order to see clearly, rays of light entering the eye parallel, entering from an infinite distance, converge precisely on the retina. In hyperopia, there's insufficient converging power in the front of the lens in the front of the eye for the rays of light to converge completely by the time that they hit the patient's retina, so that we can think of it as being that the anterior segment is too low powered. In fact, clinically, it's often the case that the whole eye is just too short, that the retina just comes too soon in the convergence of the rays of light. In myopia, the rays of light converge in the vitreous rather than onto the retina, and it is because there's too much converging power in the front of the eye. But again, it's often the case with myopia that the patients have what's called axial myopia, meaning that the eye is simply too long, that the retina is too far back and is not where the rays of light converge. But from an optical standpoint, it's equivalent to say that the eye is too long or that the converging power of the anterior segment is too high. Now, in the case of a myopic patient, there is a point that the patient can see clearly. Let's go back to the previous slide. Let's look at the right-hand side of the slide, the myopic eye. We have rays of light coming in from an infinite distance, and they converge here in the vitreous. Now, you'll remember from our discussion of conjugate planes that if we move an object to the right, that will also move the image to the right. Not necessarily at the same rate, but they'll both be going to the right. What we're going to do in the case of this myopic patient is move the object in from infinity to some finite distance from the eye. And when we do that, the image that is formed will also move a little bit to the right. And as we continue to move the object further to the right, from some discrete far distance to a closer and closer distance, the image will also move further and further to the right, approaching the patient's retina. And at some point, we'll have an image that is sufficiently close to the patient's eye so that the rays of light converge appropriately on the retina. And that's shown in this diagram here. So for a myopic patient, a non-astigmatic myopic patient, there is a point in discrete space in front of the patient's eye that is appropriately imaged onto the patient's retina. And we can sort of think of these almost as conjugate planes, where one plane is this discrete non-infinite distance in front of the patient's eye as the object plane, and the image plane as the patient's retina. If the patient accommodates, he will be adding even more converging power to the front of the eye. To an already overplussed eye, he'll be adding plus. So accommodation is not going to allow this myopic patient to see anything further than this point that is conjugate to his retina. In fact, this is the furthest point, the furthest plane that the patient can see clearly without spectacles. And we refer to this furthest point as the patient's far point. So the patient's far point is in front of his eye in the case of a myopic patient. Let's view this diagram in a little bit of a different way. The patient has too much plus power in the front of his eye. That's why the images tend to converge in the retina converge in the vitreous rather than on the retina. If we create a situation in which we have not zero vergence, not parallel rays of light coming into the eye, but minus vergence rays, those minus vergence rays, those diverging rays, are going to counteract some of the overplusness of this patient's anterior segment. And the combination of minus vergence rays of light coming in with an overly plussed anterior segment is going to result in the rays of light appropriately converging on the patient's retina. And we can create a situation in which we have minus rays of light coming into the patient's eye by having a far point that's in front of the eye. We can also create the situation by having an object that's at an infinite distance and introducing a correcting lens that's in front of the patient's eye with a minus vergence that mimics this situation here. With a hyperopic patient, the far point is in back of the patient's eye. Now, this does not mean that the patient can see in back of his head. What this means is that there's too little plus power in the front of the patient's eye for the rays of light to appropriately converge on his retina. So in order for rays of light to appropriately converge on the patient's retina, the rays of light must already be to some extent converging. So they must enter the eye with already a plus vergence. And if we extrapolate these rays backwards, we can see that they do converge to a point, and we're going to call this the far point, even though this point is in back of the patient's eye. We can, of course, mimic this situation too by having the patient look at an infinite distance and introducing a correcting lens. This time the lens is going to have plus power in order to mimic the situation that we have here of plus rays of light coming into the patient's eye. Now, let's take the case of a -2 diopter myope. And I'm going to take the liberty here of pretending that a -2 diopter myope means -2 diopters at the cornea plane. In fact, it does not. And when we deal with vertex distance later on in the series of lectures, we'll see that there's an important distinction between someone who's -2 at the spectacle plane and someone who's -2 at the corneal plane. But for low refractive errors like -2, it effectively doesn't matter. So we're going to have that conversation later. For the time being, let's pretend that a -2 myope means that it's someone who wears -2 spectacles and someone who needs a vergence of -2 striking his cornea. A vergence of -2 striking the cornea can also be achieved without spectacles by looking at an object that is a certain number of meters from the patient's eye. Now, you'll recall from our discussion of vergence, -2 always and forever means the same thing. It means that the rays of light converge. 2 means half a meter, and minus means to the left. So the rays of light are converging half a meter to the left. That's giving us the location of the patient's far point. This distance here in meters is 0.5 meters. We can create an identical situation a nearly identical situation by having the patient look at an infinite distance and introducing a correcting lens that is -2. Now, here's my question. We know that the patient's far point is half of a meter from the patient's eye. Where is the secondary focal point of this correcting lens? You'll remember that secondary focal points for plus lenses are to the right of the lens, and for minus lenses are to the left of the lens. So in this case, the secondary focal point of this lens is going to be to the left. It's a -2 lens. It means it's going to be half a meter. So to correct this -2 myope, we need, and we want to figure out what sort of lens we want to introduce, and we know that where the patient's far point is. This would obviously be an unusual situation in clinic for someone to come in and tell you where his far point is, and for you to pick a lens, although it can be done. Not advisable, but it can be done. The appropriate correcting lens has its secondary focal point co-located in space with the patient's far point. Now, the far point is immutable, but the lens doesn't have to be. And let me give you an example straight out of the Bellevue Clinic. Let's say that this patient comes in and he says, I see perfectly fine with my -2 spectacles, and they're lovely and everything's great, but I'm a professional clown. And I need spectacles that are mounted not at the normal spectacle plane, but I need these big clown spectacles that are going to be mounted 1/4 of a meter from my eye. And you say, that's no problem. Of course, one thing that we're not going to do is we're not going to have these bozo glasses be -2 spectacles. Because, as we've just figured out, the secondary focal point of the correcting lens, regardless of where in space that correcting lens is, the secondary focal point of that correcting lens has to correspond in space with the patient's immutable far point. So, if we're mounting the spectacle not at the normal spectacle plane, but at 1/4 of a meter from the patient's eye, which also happens to be 1/4 of a meter from the patient's far point, the other way, what is the appropriate correcting power of this lens? So we need this lens to have its secondary focal point 1/4 of a meter to the left. A secondary focal point to the left means a minus spectacle. And 1/4 meter by vergence means that the vergence of the lens, that the dioptric power of the lens has to be 4. So if this patient, who is a -2 myope, wants to start wearing bozo spectacles mounted 1/4 of a meter from his face, the appropriate power for these bozo spectacles is going to be -4, because we're 1/4 meter from the patient's far point. Now, it doesn't often happen that patients come into the office wanting to wear bozo spectacles, but it does often happen that patients come into the office wanting to go to contact lenses from wearing spectacles, and we have to account for the distance between the correcting lens and the eye, which is different in spectacles from what it is with contact lenses. And we'll be talking about this a little bit later on, but I want you to understand the concept of vertex distance, which is the distance between the eyeball and the correcting lens. the concept of vertex distance now, and the idea that we can always solve for the appropriate power of the lens by making the secondary focal point of that lens correspond in space with the patient's far point. Okay, let's take the case of a +2 hyperope. Well, it's the same thing. A +2 hyperope is someone who needs a vergence of +2 entering his cornea. Again, that's not necessarily true when we talk about correcting for vertex, but let's take it as granted that this patient needs a vergence of +2 entering his cornea, or +2 at the spectacle plane. If we know that the patient's far point is 1/2 of a meter in back of his eye, and we know therefore that if we know that the far point is 1/2 of a meter in back of the patient's eye, and we want to choose a lens that has its secondary focal point 1/2 of a meter in back of the patient's eye, what is the power of that lens going to be? Well, the secondary focal point is to the right of the lens if the lens is a plus lens. And 1/2 a meter means that the absolute power of this lens must be 2, +2. So +2 will give us a lens whose secondary focal point corresponds in space with the patient's far point. Now, let's say that this person also wants to be a professional clown and wants to wear spectacles also that are 25 centimeters from his cornea. We need to pick a lens that is going to have its secondary focal point corresponding in space with the patient's far point. Well, the far point doesn't move if we move the spectacles. The far point is really a function of the eye. But now we need a lens that will have its secondary focal point 1/2 of a meter in back of the patient's eye, and the lens itself is 1/4 of a meter in front of the patient's eye. So we need a lens that is going to have its secondary focal point 3/4 of a meter from the lens. So what we're doing is we're moving the correcting lens, this green guy here, out to the left, so that it is now 1/4 meter from the patient's eye. So 1/4 meter, which is this distance, plus 1/2 meter, which is this distance, is equal to 3/4 meter. So we need a lens that has its secondary focal point 3/4 of a meter to the right. A secondary focal point to the right means a plus lens. 3/4 meter means that the dioptric power must be not 3/4 but 4/3. So the correcting lens would be plus 1.33. A little bit interesting here. We've seen that as we've gone from the spectacle plane to the bozo plane in the myopic patient, that we had to give him a more myopic lens. And with a hyperopic patient, that we had to give him a less hyperopic lens. So in both cases, we are making the lens more minus, or making the lens less plus. Again, we don't typically go from the spectacle plane to the bozo plane, but we do go from the spectacle plane to the cornea plane. And as we do so, we're doing the opposite from the movement to the bozo plane. And in both cases, we are going to be adding plus to the correcting lens. The appropriate contact lens is going to wind up being more plus than the correcting spectacle, or less minus. And again, optically, that's the same thing.